We've already started into Unit 3 on chemical bonding, but one learning outcome that we'll look in a moment is going to be completed independently by listening to this video, as well as working on the independent learning worksheet that's provided on the DC Connects course. As well, you can always go to your textbook section 1210. The learning outcome for this section is you should be able to determine the shape of selected molecules using Vsepr theory. Before we go any further, talking about the shapes of molecules, I want to remind you that we've been talking about various compounds in class. When we're dealing with shapes of molecules, molecules is referring to chemicals that are bound together via covalent bonds. These differ from ionic compounds where there is the gain and loss of electrons. In this case, we're dealing with molecules, covalently bound atoms that are sharing electrons. The electrons that are being shared between atoms of a molecule are all negatively charged. Therefore, the pairs of electrons that are being shared and surrounding the atom repel each other. This is referred to as the valence shell electron pair repulsion, or Vsepr theory. The theory states that the electron pair geometry indicates the arrangement of bonding and non-bonding electron pairs around the central atom. This sounds somewhat complex, and we'll look at an example in a moment to make it a little bit clearer, but really all it's saying is that because electrons are all negatively charged, they're actually trying to get as far away from each other as possible. Thus, it affects the shape of the resulting molecule. So in the end, the molecular shape indicates the arrangement of the atoms around the central atom, and it's all as a result of electron repulsion. So let's look at an example. Let's draw the electron dot diagram for H2O. We have one oxygen. And oxygen, if you look up on the periodic table, has 1, 2, 3, 4, 5, 6 valence electrons. Additionally, there are 2 hydrogen atoms. Here's one here. And again, looking up on the periodic table, we can see that the hydrogen has 1 valence electron. The second hydrogen also has 1 valence electron. If we were to draw the electron dot diagram that actually represents H2O completely, we would move this hydrogen into this spot and the second hydrogen into the spot here. And what we would then see is that the oxygen now has a full outer valence shell of 8 electrons, and the hydrogen have full outer valence electron shells of 2 electrons. Within this molecule, there are 2 different types of electron pairs. The first are bonding pairs. The bonding electron pairs are pairs of electrons that are involved in the covalent bond holding 2 atoms together. So these are pairs of electrons found between the oxygen and the hydrogen that are being shared and ultimately forming the covalent bond. The other kind of electron pairs are the non-bonding pairs. These non-bonding electron pairs, sometimes referred to as lone pairs, are pairs of electrons not involved in the covalent bond. In this case, these 2 pairs of electrons are pairs of electrons that were provided solely by the atom of oxygen. The Vsepr theory then states the electron pairs, both the bonding and non-bonding, will arrange themselves in space the furthest apart as possible because the electrons are negatively charged and repel one another, as we mentioned previously. The repelling of these electrons then determines the 3-dimensional shape of the molecules. Let's look at a few of the different shapes of molecules that the Vsepr theory predicts. Let's draw the electron dot diagram for methane, CH4. We have 1 carbon atom, and there are 1, 2, 3, 4 valence electrons for carbon. And hydrogen, as we've seen before, have 1 valence electron. In a molecule of methane, there are 4 hydrogen atoms. These atoms then form covalent bonds in this fashion. And what we will see here is that there are 8 outer valence electrons for carbon, and there are 2 valence electrons for each of the hydrogens. Thus, each atom is satisfied in terms of a full outer valence shell. Before we move on, notice that there are 4 bonding pairs of electrons. Methane, CH4, then has 4 pairs of bonding electrons around the central carbon atom. And in 3 dimensions, if we were to look at this molecule, all those electrons are being repelled as far away from each other as possible. We would form a tetrahedral molecule. Notice the angle between each of the bonding pairs in 3 dimensions is 109.5 degrees. Now, let's draw the electron dot diagram for ammonia, NH3. Nitrogen has 5 valence electrons. We have 3 hydrogen atoms, again, each with 1 valence electron. And now what we notice is there are 8 outer electrons around the nitrogen, 2 for each of the hydrogens. There are 3 bonding pairs of electrons and 1 non-bonding pair of electrons around the nitrogen. In ammonia, then, the central nitrogen is surrounded by 3 bonding pairs and 1 non-bonding pair. The electron pair geometry is tetrahedral, but the molecular shape, because of that non-bonding pair, is actually trigonal pyramidal. Notice in this case, because of the different numbers of bonding pairs and non-bonding pairs of electrons, that the angle between the electrons bound to the hydrogens and nitrogens is 107 degrees. Now, let's go back to the diagram for water. This is the diagram we arrived at earlier on in the lesson. Notice there are 2 bonding pairs of electrons and there are 2 non-bonding pairs of electrons. In water, the central oxygen atom is surrounded by 2 non-bonding pairs and 2 bonding pairs then. And the electron pair geometry is again tetrahedral, but 2 of the pairs are non-bonding, and so the molecular shape itself is bent. Notice the angle between the electrons, the bond between hydrogen and oxygen, is 104.5 degrees. Finally, let's draw the electron dot diagram for carbon dioxide. The central carbon has 1, 2, 3, 4 valence electrons. And if we look at each of the oxygens here, they each have 6 valence electrons. In this case, the bonding is slightly different than we've already looked at. The oxygen and the carbon will actually share 2 electrons from each atom, as indicated in the image here. Notice that each oxygen has 2 non-bonding pairs of electrons. And the carbon has 2 bonding pairs of electrons on each side, so 4 bonding pairs. This is a slightly complex image, so let's look at one atom at a time. Let's look at the oxygen on the right side here. We can see that it has 2 non-bonding pairs of electrons and 2 bonding pairs. In total, there are 8 electrons surrounding this oxygen, and so its valence shell is satisfied with 8 electrons. The same is true for the second oxygen. 2 non-bonding pairs, 2 bonding pairs, and a total of 8 valence shell electrons. Looking at the carbon, we can see that there are actually 4 pairs of bonding electrons. There are 8 electrons in total in the valence shell of the carbon. Overall, we have a slightly different diagram than we've seen previously. So in carbon dioxide, the central carbon atom is bound to each oxygen by 2 electron pairs. This is a special kind of bond we haven't looked at yet, called a double bond. According to Vsepr theory, the electron pairs will repel each other, and they will be at opposite sides of the carbon atom to get as far away from each other as possible. Thus, the electron pair geometry and the molecular shape are both linear, as shown in the image here. You can see in this case the 2 white bars are indicating the double bonds between the carbon and the oxygen atoms. In the end, there is a summary of the Vsepr theory in table 12.1 of your textbook. Notice the relationships between the bonding and non-bonding pairs, the molecular shapes, as well as the bonding angles and example molecules for each of the shapes. So in the end, the learning outcome that we've satisfied here are that we should be able to determine the shape of selected molecules using Vsepr theory.